One splice, two measurements, from one direction, minus 0.29 dB, from the other, plus 0.34. If we saw only the first result, we would have to believe that a splice can amplify light. If we judged only the second, a very good splice could look suspicious. Both readings are real, but neither one on its own shows the actual splice loss. So let's run the complete test. On the INTERLAB test bench, we have two lengths of fiber joined by a single splice and a Yokogawa OTDR. First, we measure the link from side A. We save the trace, swap the fiber ends, and run the second measurement from side B. The test conditions stay the same, a wavelength of 1310 nanometers, the same pulse width, refractive index, and averaging time. These are not two different splices or two different test setups. The only thing we change is the direction from which the instrument sees the same event. We start in the A to B direction. The event table places the splice at roughly 6.4 kilometers. The measured loss is minus 0.29 dB. On the trace, the event appears as a clear step upward. The backscatter level after the splice is higher than the level before it. For now, we do not interpret the number. We simply save the trace exactly as the instrument measured it. Now we swap the ends and measure the same splice in the B to A direction. This time, the trace steps downward and the event table shows plus 0.34 dB. We did not remake the splice between measurements. The fiber and the instrument settings did not change. We only changed the end from which the test was started, so now we have two different results for one unchanged connection. Let's overlay the two traces. At the splice, one moves upward and the other moves downward. Now we calculate the arithmetic mean. Minus 0.29 plus 0.34 divided by 2. The result is 0.025 dB. Just 25 thousandths of a decibel. This is our best estimate of the actual splice loss. Not the negative value, not the higher positive value. The result calculated from both directions. Why does averaging work? The answer lies in what the instrument is actually seeing. An OTDR is not measuring the light after the splice with a power meter. It sends a pulse into the fiber, then listens for a tiny amount of light scattered back toward the instrument. The height of the trace represents the level of that returning signal, but two fibers can return different amounts of light even when both carry the forward signal perfectly well. The instrument therefore sees two things at the same time: the actual splice loss and the backscatter difference between the fibers on either side. In the A to B direction, we move from a fiber that returns less light to one that returns more. The trace steps upward and the instrument calculates a negative loss. Reverse the direction and the backscatter difference works the other way. The trace steps down while the reported loss becomes positive and too high. This directional error has the opposite sign in the two measurements. Averaging cancels it and leaves the loss of the splice itself. A gainer does not amplify anything. It is simply how two different fibers can look to an OTDR. 3 practical rules come out of this test. First, a negative event loss does not mean that the splice is amplifying light. It points to a backscatter mismatch between the fibers. Second, to evaluate a gainer properly, test the splice from both directions and average the two results. Third, both traces need matching settings and clean sections of trace around the event. Average comparable results, not two random readings. A one-way trace is still excellent for locating an event. It is not always enough to evaluate its loss accurately. An OTDR is not an automatic pass or fail machine. Its result depends on fiber physics, instrument settings, and the way the test was performed. If you want to understand traces, dead zones, pulse width, and bidirectional testing in more depth, visit the free INTERLAB Fiber Optic Measurement Academy. Go to interlab.pl/academia. Change the parameters in the simulator and watch the physics respond in real time.